Good morning, everybody. We'll get started here in just a few minutes. If you can please text in a head count of everybody on your screen that's watching, I'd be appreciative. Also, if you can sign in with that QR code, that'd be great. Thank you. All right. Good morning, everybody. Hope everybody's awake, ready to learn something this morning. If you didn't hear me before, if you can please sign in with that QR code and also send in your number of people that you are attending with on your screen. That way we can get a kind of a head count of who's all joining us this morning. Okay, so this is a topic that comes up every spring: airflow, refrigeration. What is the correlation between the two? So for some of you that have already joined in on some of our amazing trainings that Tech Services is putting on, got someone saying no sound. Can everybody else hear me okay? Looks like Michael. Okay, looks like everybody can hear me. Okay, so Tech Services is putting on some trainings here this spring. This is a condensed, shortened version of that training. A lot of us techs and installers get hung up on the importance of airflow and refrigeration. So we've had some trainings over on the West Coast that Jamin has put on, did an amazing job. We have Michael is out doing trainings this week, as well as Dan in our Montana, Oregon areas. So if you have not signed up yet, we do have some trainings here in May for Yakima, Wenatchee, Kennewick, Spokane. If you can get into those classes, they fill up very fast. So this is going to be a condensed, shortened version of that. Airflow and refrigeration, very important. So for those of you that are familiar with the refrigeration cycle, here is just kind of a breakdown cutout version of this. You can see this unit is in air conditioning mode. High pressure, high temperature gas goes to our outdoor coil. We are evaporating, or we are expelling the heat from that outdoor coil. Condensed liquid refrigerants flowing to our indoor coil. We boil off that refrigerant to a low temperature, low pressure gas that absorbs the heat from our indoor air. Mind you, cooling mode. We're going to talk about the effects of airflow on refrigeration. We are not going to dive in too deep on airflow. We're also not going to dive too deep on refrigeration. This is simply just focusing on the effects that one has on the other. So this is a very short version of the refrigeration cycle. Mind you, this is in cooling mode. In heating mode, it is reversed. We do have two metering devices on a heat pump system, both of which are at coils, one on the indoor coil, one on the outdoor coil. This is an easy way for me to understand it. This is a kind of a complicated process. So I like to try to make it as simple as possible. When we talk about the evaporator, that is the heat absorber. It is absorbing the heat to keep that low pressure, low temperature refrigerant from freezing. So we are absorbing the heat. That could be your heat pump in heating mode. That could be your evaporator on your indoor coil in cooling mode. Now we have our metering devices. They could be an electronic EEV, like electronic expansion valve. That could be like this one shown here, where this is a thermostatic expansion valve that's mechanical. Its job is to meter the refrigerant by reducing the pressure. It is the pressure decreaser. It is reducing that high pressure, low temperature liquid. It is decreasing the pressure. And so any restriction, any kink in the system will do the same thing. Those of you that have seen frost on refrigerant lines, that's what it's doing. So without proper airflow across those frosty lines, it's going to freeze. We've got our compressor. That is the pressure increaser. It increases the pressure of gas. It cannot pump liquid. This is not a water pump. It can only pump vapor refrigerant. Then we've got our condenser. That is the heat rejector. That could be the condenser in cooling mode on our outdoor unit, rejecting the heat from the high pressure, high temperature gas. That could also be the indoor coil in heating mode on a heat pump. It is actually rejecting the heat into the airflow, and that's where we're getting our heat from. So evaporator, metering device, compressor, condenser. We have metering devices that are indoor and outdoor coils if it's a heat pump. And the evaporator and the condenser do change with operation. So your evaporator will always be your low pressure, low temperature coil, and your condenser will be your high pressure, high temperature coils. So let's keep it simple. Let's just remember this process as we're working on all sorts of different equipment, whether it's single stage or variable speed. Some things to know. Let's keep this simple. Suction pressure is evaporator temperature. That could be your gas line in cooling mode. That could be your true suction port on your heat pump in heating mode. Okay, so suction pressure is evaporator temperature. Liquid pressure is condensing temperature. Okay, the evaporator coil, when you see high superheat, and I know I've talked to a few of you on the phone this week, when you see high superheat, the coil is not as full of refrigerant. It is empty. It's more gas. When it's lower superheat, the coil is more full, right? So we have more refrigerant in that coil. So keep that in mind. Now, when we talk about subcooling, subcooling is how much liquid refrigerant are we stacking in the bottom of that condenser coil. Higher subcooling, more liquid stacking. Lower subcooling, less liquid stacking. So we know that metering devices need a full liquid line full of liquid refrigerant to the metering device before it works. If we do not have liquid refrigerant to that metering device, it cannot do its job. If there is a kink or a clogged filter dryer with some sort of restriction, it is now becoming the metering device. We are reducing that pressure. So you can have a clogged filter dryer from our outdoor unit to our indoor coil that is causing that pressure reduction. It's going to cause that refrigerant to boil off, and we're going to be metering the device, metering the refrigerant before we get to the metering device. So let's just really break down the basics. Suction pressure is evaporator temperature. Liquid pressure is condensing temperature. What is happening in our evaporator coil? Mind you, that is our low pressure, low temperature refrigerant. And what is happening with our subcooling in our condenser coil? How much do we have How much do we need? Any subcooling is a good start. No subcooling means we are not going to be able to meter. So let's keep this in mind. Now, what is the relation between the two? Um, when you are measuring airflow, when you call into tech services and we ask you, hey, what is the airflow? We are looking for a number. We are not looking for an opinion. We're not looking for it's good, it's perfect. We need a number because we have the tools to test it. And if we don't know, we're assuming. So airflow is so critical in the system that if we do not have proper airflow across either one of our coils, we're not transferring heat. We're not able to move the energy we need to. And keep in mind, we are always adding and removing heat. We're not adding cooling. We are removing or adding heat. So clog filters, clog coils, clog registers, we've all seen this. We've all seen these in the field. If we have these kind of restrictions, our system performance is going to be lacking. So please, I hope this doesn't look too familiar for us unless we're there to make it right. But these are all far too common systems that we see out there, especially when we start utilizing flex duct. Flex duct is a great product used in the right scenarios. When you see flex duct is restrictive. Think about going down a slide as a kid. If we added a whole bunch of bumps and ribs to that slide, it is going to be a lot harder for you to go down that slide than if it was slick and smooth and you were able to just scoot down that thing. Same thing with airflow going through ductwork. The right amount of airflow, that is how we're able to maintain comfort. That's how we're able to have better air quality. This is how we're preventing our equipment from overheating. This is how we keep our energy down. And more importantly, this is how we maintain the longevity and the lifespan of our equipment. Bad airflow is like driving your car with the brakes on. Something's going to fail. It's just what and when. So here's a couple little illustrations to look at. You can see the unit on the left, 400 CFM per ton. That is our target charging airflow. As you can see on the condenser coil on the one on the left, we've got a little bit of a red coloring. It's just kind of showing we've got a happy unit. The one on the right, still operational. We got a little bit more heat, a little bit more liquid subcooling stacking on our outdoor unit. When you take these two scenarios where we have 400 CFM per ton and 325 CFM per ton, are these both acceptable operating equipment? The answer is yes, but it's also no, depending on your location, depending on your circumstance, depending on what your target is. 400 CFM per ton is our target charging airflow. Keep that in mind. That is not our target setup. That is not our target operating parameters. That is our target charging airflow. So when we set up a unit, we want to set it to 400 CFM per ton to ensure the unit is properly charged. Once we get into what our target operating parameters are based off your location, based off what we're trying to achieve, we may want to move more airflow. We may want to move less airflow. So when we've got a system running at 400 CFM per ton, we've got an equal balance between our output capacity, our sensible capacity, and we're able to monitor our latent load moderately. We'll go into a little details of what your sensible and your latent are. When we have 325 CFM per ton, we're actually able to manage both sensible and a lot more of our latent load. Latent heat load is your humidity. That is literally the condensate draining down on a unit in cooling. When you get into areas that have high relative humidity, we are looking at a much higher latent load. So we'll go into a little bit more details on different areas. We'll go into a little bit more detail on what CFM per ton our target could be. But for those of you that have ever done total heat capacity loads, when you take wet bulb supply, wet bulb return, plot those on an enthalpy chart based off of your pounds of water, you're able to find what your total heat capacity is and then use your dry bulb. Dry bulb is your typical supply return temps, what your thermostat sees, your sensible load. And you can actually do a calculation on what your total capacity is. Most of us will do a simple, 1.08 times CFM times delta T. There's your sensible load, right? But without using wet bulb, you really can't find what your latent heat load is. And a lot of us forget that in most circumstances, if our indoor relative humidity is over 40%, we could lose up to 30% of our total system capacity to just our latent load. So if you walk into a home that's 40% humidity because they're trying to add humidification for plants, for maybe some exotic animals, things like that, if we have higher humidity within the home and we're not able to remove that humidity, a simple 2-ton unit could run at 18,000 BTUs sensible load, and just because it's trying to fight that humidity. So some things that we want to really keep in mind when we're looking at equipment. Now, when we're talking 400 CFM per ton, there is a problem with that rule that if we just assume and we don't look at what we really need for our areas, it could really put us in the weeds. Now, the 400 CFM per ton design, it's been used for years. It's an adequate baseline for airflow on many types of equipment in many moderate climate zones. Here in the Pacific Northwest, we have high mountain desert, we have low valley desert, we have coastal, we've got dry, we've got humid, not too humid, but we can get in some humid areas. So we're going to really want to keep in mind of where we are. A few examples of where we may need to adjust our airflow, our CFM per ton, are areas like higher altitudes where the air is less dense. Therefore, when we have less dense airflow, more air is actually required to maintain the same mass flow rate over that coil. Same thing with when we start derating our gas equipment, it's just different at higher elevations. The nominal or what's listed for tonnage on that piece of equipment often is not what the equipment produces at a current load condition. So just because it's a 2-ton system that's designed for, let's say 95-degree outdoor, 80-degree indoor return air temperature, it can easily produce under 20,000 BTUs at 73-degree indoor and 97-degree outdoor temperatures. And your CFM per ton will actually be much different than intended. So in that case, you'll need to be running a higher CFM per ton due to the reduced capacity at those load conditions. So areas that have higher latent heat loads, higher humidity loads, they'll run lower than 400 CFM per ton on purpose to remove that moisture from the air. In areas like, let's say, Phoenix, Arizona, for example, very arid, very dry climates will often run higher than 400 CFM per ton in those areas because there's less latent load, there's less humidity and less moisture from the air. So we really got to keep in mind on what we are trying to achieve as far as airflow. 400 CFM per ton is a good baseline rule. That does not mean it matches the AHRI approvals for that equipment. You might find that an AHRI match, what you would see like on our Quest Resolute systems, a 3-ton unit, I believe the AHRI match on that's about 1,000 CFM. Well, that's like a 2.5-ton load capacity at 400 CFM per ton. So we really want to look at what our AHRI matches are before we really start raising some red flags. Because as we know, whether it's heating or whether it's cooling, our sensible delta T, our dry bulb delta T, if we decrease airflow, we increase our delta T, our sensible dry bulb readings. We've all seen it. If you haven't seen it, give it a test. Change your airflow. You're going to see delta T increase. And the math after the equal sign will not change too much when we are increasing or decreasing airflow. But we have to keep all these things in mind when we're charging equipment. We can't charge equipment at 300 CFM per ton and say that our refrigerant flow is proper, because we need to charge at 400 CFM per ton first, then adjust our airflow as needed. And this is something that we go in great detail on when we do our spring trainings. So highly recommend that you guys get a part of that as much as you can. When we start talking about the evaporator, how does the evaporator absorb heat, right? So these are fun little illustrations. I cannot take credit for these. These are just information that are out in the HVAC world. This is part of our, when you're part of this, you know that there's just an endless amount of information out there. And I really challenge you to, when you have a question or you have, you need a little bit more understanding. There is a world of information out there that you can find, and you can always reach out to us, and we're always willing to help. So when we start talking about how the evaporator absorbs the heat, right? So in heat pump and cooling mode, the indoor coil is going to be the evaporator, and the heat pump in heating mode, the outdoor coil is going to be the evaporator. So the heat gained in the evaporator, in these scenarios with the indoor air being moved over the evaporator, the air is warmer than the refrigerant in cooling mode. So the heat leaves the air as it impacts the tubing and the fins on that coil, because, well, hot goes to cold, right? The air temperature is decreased because the heat is removed from the air as it moves into the refrigerant. Remember, we're adding or removing heat. The refrigerant in the evaporator is at saturation, it's at boiling. The coil temperature doesn't directly change as heat is added to the refrigerant, but it begins to increase indirectly. So as the total heat energy in the evaporator increases, so does the coil pressure, and vice versa. So this is similar to, let's say, like a pressure cooker. As the water boils in that pressure cooker, the pressure increases, and so does the boiling temperature of the water. We can get stuck in the weeds when we really look at what's happening, but this is just a very surface understanding of how that evaporator is absorbing that heat. Hot goes to cold, right? So when you are opening your door on a hot summer day and it's colder inside, that air just shoots from outside right across your face, right? Same thing in the wintertime. Open the door and it feels like you got air coming across the back of your neck heading outside, right? So my mom was always telling you, don't leave the door open. And there's a reason for that. Hot goes to cold. So we have to really look at what is happening with that evaporator in both scenarios. Now, when we talk about latent load, right, that's how we're removing the moisture from the air. So when the coil's temperature, right, let's say cooling mode, when the coil's temperature is below dew point of the air moving over it, mind you, the evaporator coil without the blower will freeze. All you techs and installers out there, you've seen that. Dirty filters, failed blower motors, closed off registers. If we do not have enough airflow, that evaporator on that indoor unit will freeze in cooling mode. And it wants to. That's pretty much what it's trying to do. And we're keeping it from doing that by adding heat into that coil. So when the coil's temperature is below dew point of the air moving over it, there is a transfer of latent energy from the air as some of the water vapor in the air condenses to a liquid. And when it condenses into the liquid, water, condensate that you see draining away on the evaporator coil. That is the latent heat transfer, and it does not result in colder air at all. It's just, you're going to see lower moisture content in the air. That's it. That's what you're going to see. That heat impacts the evaporator in the same way as a sensible heat load is added to the total heat picked up by the evaporator. The difference is when you have a system that is moving way more airflow. Let's say we take a 400 CFM per ton system in Phoenix, Arizona, and we try to put that somewhere coastal where we have some humidity on a hot day, and we are not removing that humidity, the sensible load in the home will go down. Your thermostat temperature will go down. But if we're moving too much air, we may not be able to remove that latent load. So the home will feel kind of cold and clammy, kind of like a wet cave. It'll feel cold, but it's still going to feel humid. That could be we put a 2-ton unit on a 5-ton blower and never adjusted our airflow, or could not achieve the right airflow. Our delta T might look proper, our pressures might look proper, but if we did our delta T with dry bulb, which we usually do, and we didn't use wet bulb, and we didn't actually measure what our wet bulb was, um, we may not be removing both loads in the home. Total heat is sensible and latent. Most of the time, latent is much lower than your sensible load, unless you're in like Louisiana, Alabama, somewhere in the South where, it's 100% humidity and a 100-degree day, which just sounds awful. But we have to look at what our target is, right? So we're not looking at just design temps. We're looking at airflow, capacity, what we're doing. And so, like I said, as that coil temperature is below dew point, which it usually is, any air moving over it, that transfer of that latent energy from the air will turn into water, condensate will drain away, and the latent heat will drop down. So when you walk into these big department stores in the summertime, you walk into your Walmarts and your Costco's and your Fred Meyer on a hot day, and you're like, boy, it feels good in here. That company's not paying to keep that place 72 degrees. What they're doing is mass dehumidification. They are removing as much humidity as they can to make it feel more comfortable within that store. What they're doing is removing the latent load in that building space. So, things to keep in mind. Now, in this little illustration here, you can see this unit is in cooling mode. I cheated because it's a blue line. Man, it's pretty simple, right? So this is a very crude drawing. Please don't design your systems based off this because I don't like the way that return air and that air handler is. But like I said, this is just a cartoon illustration of some details to help us. Now, in air conditioning, it refers to the difference between the air temperature and the return air entering the evap coil and the saturated suction temperature, often called the coil temp. In typical 400 CFM per ton applications, like we've been talking about, this difference will be around 20 degrees dry bulb, right? The higher number meaning the colder the coil, and the lower number meaning warmer coil. Several things could impact this coil temperature differential. This is what we're measuring for TD, temperature differential, delta T, right? Some terminology for those unfamiliar. Several things can impact that temperature differential, including the refrigerant mass flow rate. It's a fancy word of saying how much refrigerant the compressor is moving. Remember, the compressor is a pump, right? How much the refrigerant compressor is moving, how the metering device is performing, the return air dew point, the moisture content, right? Your latent load, and most commonly and most important, airflow. So when we think about a compressor is a pump. What happens when you have a garden hose that you have one of those cheap little slinky hoses that grandma likes that automatically just coils up when you're done using it right back into this fancy little vase she's got sitting on the ground? That's great. You've got no volume flowing through that thing. You might have pressure, you don't have volume. It's the difference between having the proper size line sets hooked up to a unit and not. You're starting to see on some of these R454B units, you can use a 5/16 line set. You can do it on the liquid line. Absolutely. It is doable. But if you look at the pressure drop between a 5/16 and a 3/8, especially those of you that utilize our refrigerant piping program, you're going to see there's a much higher pressure drop on 5/16 than 3/8. That means that compressor's working a little harder. Long line sets, compressors working a little harder. Vertical changes, that compressor's working a little harder. Clogged filter dryers, it might not be causing the pressure to go down, but it could be affecting our refrigerant flow. It's going to cause that compressor to work a little harder. All of these things are how this system is moving that mass flow rate, refrigerant flow rate. So an engine that is starved of fuel won't work properly. A sprinkler that doesn't have enough water flow will not work properly. A duct that is kinked or undersized will not work properly. These are all the same parameters we're looking at when we're looking at the refrigerant mass flow rate of that compressor. If we can't move the refrigerant, we cannot add or remove heat, because that's what we're doing. We're adding and removing heat. And then we have mechanical devices. We have electronic devices that are metering that refrigerant flow. Its job is to maintain superheat in that coil. And as we looked at earlier, higher superheat, going to be less full in that evap coil. Lower superheat, more full that coil is. That's the job of the metering device. It is going to try to manage like a police officer with a traffic sign in a street in the middle of New York. It's trying to manage all sorts of things at one time: refrigerant flow and airflow. So we talked about refrigerant flow. We talked about latent load. We talked about sensible load. We talked about the importance of having proper flow and proper airflow across the system. Now we're going to talk about airflow. We're not going to dive into this too much, but I get a lot of people when they say the airflow is good, or it's a 3-ton unit. I set it at 400 CFM per ton for a 3-ton, so it's moving 1200 CFM. Is it? Right? You can trust what it says, but you should really verify it. If you ever call into tech services and we ask you, please, what is your external static pressure and what is the speed tap on that unit? This is what we are talking about. Total external static pressure. It is the pressure that is the resistance in the airflow, the air places within the system. It's what that blower sees. I know a lot of you are using a true flow plate. Awesome. I love it. That is your second way of measuring airflow. Your first way of measuring airflow is what the manufacturer wants to see. You verify it with a true flow plate. You do not use that as your primary, because there are a lot of parameters that you may not see. It's just like us using our online diagnostics. It might tell me it's moving this much airflow, but is it? Because that feedback is just based off of the RPMs and the Amtrol of that blower. I don't know what's happening in the field. I'm just looking at numbers. Same thing with you in the true flow plate. Let's make sure we are using our tools, all of them, to get the information we see. So on a gas furnace, we are measuring the pressure across the blower motor. That furnace did not come out of the box with a filter, and it did not come out of the box with the ductwork, and it did not come out of the box with the evaporator coil. You need to measure the return static on that between the filter and the unit on the return, and then on the supply before any ductwork in any coil. Okay. If you're measuring it beyond the coil, then you are not calculating the pressure drop across that coil. Most evap coils are 0.2 to 0.35 is our pressure drop across evap coil. Same thing with filters. I've seen systems where the filter alone was causing more resistance than the entire ducting system. So if you need to take a picture of this screen right here, right now, please do so. I'm going to give you another few seconds to take a picture. But this is very important on how to understand taking this. And you might get a little cheat sheet that we may send out to you to help you in the field. Fan coils, your air handlers, it came out of the box with the coil. Please do not try to measure in between. You measure on the return of the unit and on the supply of the unit. And yes, that is even before the filter on units that come with filters. This is very important. There's a little tech tip that if you've called in for me, I may have sent this out to you. This is just a really easy example of what you're seeing as far as where am I measuring my airflow. You can see there is a massive spacer between that coil and that furnace. You're probably not going to get that most of the time. You're going to have to find a way of drilling a small little hole in the side of the cabinet. Go to Harbor Freight if you need to, buy the little Christmas tree step bits, just enough to get to that sheet metal. Please do not use a 6-inch drill bit. It gives me so much anxiety when I see people do that in the field. I'm just waiting for you to go through that heat exchanger. Please don't. As you can see, this is how we are measuring our static pressure. You can use a dual port manometer, such as this. I personally have one. I have a habit of only using one port at a time. simply because I want to make sure I'm getting accurate information, and I test the supply, then I test on the return, test on the supply again. I only zero it once, and that's before I take any of my readings. So let's make sure we have the proper tools. You do not need to buy this one. You can buy, you can use a MagnaHelic. I've actually had to make a slack tube manometer in the field with some condensate tubing and a ruler just to measure difference. Whatever we need to do, but we need to get proper airflow. There's no reason we shouldn't have the right tools in the field if we're going to be doing HVAC. Once again, I cannot take credit for this awesome illustrations. These are out there. This is in the HVAC community. When we're looking at airflow, what are we looking for? We're looking for too high or too low static pressure. We're looking at what the fan airflow settings are. We are looking at the system airflow requirements. How much airflow do we need to move on the system? And do we have the airflow settings proper? We're looking at the temperatures of the equipment, whether in heating and cooling mode. We're looking at the refrigerant charge readings. We're looking at system temperatures. We're looking at combustion readings and heating. Are we running to manufacturer specs? Are we overheating in gas heat? Are we got way too high of a delta T in cooling? What are we seeing? Do we have this thing even set up right? And it starts with airflow. So if you look at some symptoms with a freezing indoor coil, what's causing that? Let's not get stuck on it, but we have to understand, well, freezing coil means we have lack of refrigerant flow or lack of airflow. Simple as that. Plain and simple. We need to figure out what is going on with there. If we have a low evaporator load, maybe the indoor airflow is just far too cold. Maybe it's 75 degrees upstairs, but we've got a 20 by 20 return grill in that 65-degree basement. And because of that, we've got a low evaporator load. We have no way of absorbing heat into that coil because there's really not much heat to do it. Maybe we don't have enough refrigerant in the system. We don't have enough refrigerant flow. We're out of refrigerant. It's going to start flashing off and boiling whatever's in that coil, and it ain't coming out because there's no way to pump it. Maybe we have low outdoor ambient temperatures. Maybe because we don't have enough outdoor temp to expel and condense that liquid, maybe we should have a low ambient kit. Maybe our blower's having issues. Maybe we have the wrong universal blower, wrong capacitor. Maybe it's set up right. Maybe we have some refrigerant restrictions. So we need to make sure we take our nose off the problem and sit back and look at the whole system, because every single aspect, including that one damper and that one location and that one register in the bathroom, yeah, it has an effect on the system. It's just how low or how high that problem could be. If you messed with any of our boards, this looks familiar to you. This is our 7-segment display on our units. Make sure the airflow is set up proper. I mean, I am not going to gauge up to a unit unless I can verify airflow, because anything I do on that outdoor unit prior to verifying airflow is an absolute waste of time. I can take a 3-ton condenser with two tons of air and make my pressures look good. I can do it. I have done it. I've had talked to people on the phone that have done it. Pressures are only a result of airflow. Make sure your airflow is set up first. S9B2, you've got to go through and set up your CFM per ton and your tonnage. And what's nice is this will tell you the airflow. It'll read out, 101 for, 1010 CFM. It might read 120 for 1200 CFM. It'll tell you what it is. But let's make sure it's set up right, whether that's a speed tap, a dip switch, a setting, right? Let's verify airflow before we do anything else. So if we take this scenario, this is a real scenario. Well, it was one I've recorded earlier this week. I've got 0.35 inches water column on my supply before my evap coil. 0.55 inches water column on my turn. That's a negative number, right? It's a positive. Get rid of that negative sign. It's a positive. 0.90 inches water column. And keep in mind, that's as high as that blower performance chart goes on that unit. So when I say you're off the charts, it physically is not on the charts. And these are what some of our blower charts look like. This is an S9B2 with a 5-ton blower. We were running a 4-ton unit. We had it set for 400 CFM per ton. And at 0.9, yeah, we were able to do it. So we have high static pressure. It is beyond what the manufacturer wants to see, right? But if we're at 0.5 inches water column with ductwork, then we added a filter that added 0.2. Then we added a coil that added 0.2. Well, there you are. There's your 0.9. That's just what happens. We're just adding restriction as we go. And you can see on a 4-ton unit, we are still moving 400 CFM per ton. It's high static, but we are moving the airflow. So let's just make sure that we're doing what we need to decrease that static pressure. Because as you can see, even if that static pressure was at 0.1, it would still run at 1600 CFM. Let's just make the load on that blower a little bit less, make it last longer, right? Because this is when blowers start getting tired and they start to fail. So 0.9 static, yep, 400 CFM per ton. It's able to do the airflow we need. Now, on the S9 V2s, the S8 V2s, your link systems, they're going to tell you on the apps what the airflow is moving at. If it says 088, it's 880 CFM per ton. You can see on this screen, it says 049. That's what, 490 CFM. That's probably in constant fan mode. But on your S9X1s, your X2s, your S8 ones, your S82s, you're going to have to set the speed tap, and it's only going to give you the speed tap readout. So you're going to have to do a little work to set that up. And no, they do not come set up out of the box. Very seldom do you have any system today that you can install it and it's good to go out of the box. You're going to have to do some work. That's just part of it. So here's another scenario for you. Our supply static after our coil is 0.05. Our supply before the coil was 0.35. So we've got a 0.3 inch water column pressure drop across that indoor coil. We had 0.55 inch water column on our return. Having less than 0.10 inches water column on our supply, is that enough static pressure? Is that enough supply static to actually balance the system? So remember, the further away we get from this furnace, the less supply static we have. So if this poor furnace is trying to overcome so much restriction from the filter, from the return duct, from that indoor coil that we have lacking supply static, it's like having 4 or 5 sprinklers hooked up to one garden hose. What's going to happen to the sprinklers at the far end of that line when there's not enough volume, not enough pressure to get there? They're just going to kind of piddle out of the end, not much, right? Same thing when we talk about balancing a home. So when you get a home that's got those extremity rooms that are, they just don't seem to heat properly and they don't seem to cool properly, perfect. Go back to your unit because it all starts there. If you have less than 0.10 on your supply static, you're going to have a hard time balancing that system, a really hard time. So we got to keep that in mind. Now, let's say we were able to put in a better filter. Maybe we looked up in the return grill and we saw that in place of what should have been a hard elbow was a 16-inch or an 18-inch flex duct just kinked over on the return grill. And maybe we went up there and replaced that piece of flex. We pulled it tight. We removed the 15 feet of flex duct that was just left up there because no one ever pulled it tight and got rid of the remainder. And maybe we put a hard elbow and we got rid of this very restrictive filter and we put in a proper filter that will do its job, and we were able to decrease that static pressure on the return. Well, that means we have more supply static. And if we're able to get our supply static down, that means we're able to have more balancing static or your supply static to the system. If we're able to do that, then we have more to work with, right? But the same thing, we don't want too much supply static because of that could be very noisy, right? Now we're dealing with velocity. We could be dealing with whistling registers. You think about a mobile home. The supply ducting on a mobile home is so bad, there is no return. The return is the louvered door that goes by the cat's litter box next to the laundry room, right? I mean, that's the return duct. And all the supply static is so terrible and so restrictive that we don't have room for supplies or return duct. So when you talk about mobile home rated, kind of keep in mind what goes into that. So when we start looking at this situation, having 0.10 on our supply and negative 0.15 on the return, right? Wait a minute, that doesn't seem right. I have this thing set for 400 CFM per ton. Why do I have such low static? This blower is trying to run. Are we even moving any air? What if the blower wheel's clogged? What if it's not grabbing air to move it? What if the indoor coil is clogged, right? If the indoor coil is clogged, I'd like to think we'd have really dirty supply stat or really high supply static before that coil, but it's got to go through the furnace first. So what if the secondary heat exchanger is also clogged? That means that blower motor is not moving any air through the secondary heat exchanger, right? So we can't have any supply static. So you got to keep in mind, like, what is happening? What are some variables that we can remove to get an idea on this, right? You got to think about it. It's like a car on the ice. Um, your speedometer might be saying you're going 90 miles an hour, but you look out the window and you got people walking past you. Okay, don't trust everything. You need to verify it. So just like a car spinning its tire on the ice, and that blower is moving the RPMs, are we actually moving the airflow? We need to see that. We need to understand, are we actually moving the air? So don't get caught in the weeds. We need to look at our equipment. Now, when we were talking about a little bit previously, we were talking about different climates. These are some of the climates that you can see out there. Dry, arid climates, cold, dry climates, higher altitude, right? When you're looking at your systems, do we need to move 400 CFM per ton? So this is what we were talking about when we came to latent loads, right? So keep in mind your area. This is stepping back a little bit on elevation, indoor humidity, outdoor humidity ratings, right? So along with, are we moving air? Can we move the air? And what kind of airflow are we moving? Once we have our system charged, then what do we need to do, right? So we need to really look at what we need to set this system up for. Now, since we talked about airflow, we talked about how to measure airflow. We talked about the importance of it, proving it right, proving it wrong, seeing if we have too high or too low static pressure and what it means. What happens when we decrease the airflow? And you guys have all seen this. Anybody that's been in the trade for long enough or has even touched your first unit on a diagnostic, you have seen this information, whether you knew what it meant or not. So if we decrease airflow in cooling, our evap coil temperature starts to decrease. And when we decrease our temperature in our evap coil, we're starting to freeze. If that evap coil drops below dew point, which it is, and we're removing that humidity, but if we go too far, we can freeze. And you might see some water at the bottom of the cabinet or splashed around inside the unit because, well, any of that water was trying to drain away, can't drain away on a coil that's frosted. It'll actually drain off if it doesn't freeze. So you're going to see your suction pressure drop. Your TXV is trying to maintain superheat is going to go, whoa, I need to start throttling back. And since that compressor is a pump and it's trying to move refrigerant, and that TXV is throttling back, now we have low suction pressure, we have high superheat, and we're going to have high subcooling. We're going to be stacking more liquid refrigerant on our outdoor coil. We're going to put more pressure on that compressor. We're going to have higher wattage. We're going to have a system that is trying to do 90 miles an hour, but someone's pulling on the parking brake. That's what's going to happen. So, in all things considered, what your customer is going to feel is their sensible capacity is going to be lower. That unit is no longer moving the airflow and it's no longer moving the refrigerant. We can literally take a 3-ton system and downsize it to a 2-ton, a 1.5-ton by not moving the refrigerant and not moving the airflow. All we're doing is it's speed, it's mass, it's energy. We're moving energy in and out of the home with airflow, and we're moving energy in and out of our condenser with refrigerant. If we slow that down on either parameter, so does our capacity. We are no longer doing, I mean, might as well turn them both off. Stop moving refrigerant, stop moving airflow, you stop having sensible capacity in operation. It's that simple. You decrease your airflow, you're slowing down one of your wheels. You're starting to slow down. You slow down your refrigerant because you've got a metering device slowing it down, or it's undersized, or your condenser fan motor is not working, or your compressor is getting weak. We stop moving energy. And if we're not moving mass, we're not able to add or remove heat. And then we're going to get, go back there, and then we're going to get higher head pressures on our condenser. I mean, you can see the unit on the right versus the unit on the left. The one on the left's a little angry, right? A little more stacked refrigerant. Our outdoor unit, we're going to have higher head pressures. You're going to see that. You're going to see poor compressor lubrication simply because we're not moving refrigerant. That cold, low pressure, low temperature refrigerant that's coming back to the compressor is to cool it down, right? If we're not moving refrigerant, we're not cooling it down. It's like a car engine with lacking water pump or lacking coolant. It's just not going to cool it down. The compressor is going to run at a much higher wattage. you've ever got the 18405 error codes on variable speed units, that's what that is. The compressor is running at a much higher wattage than it's supposed to. Is that airflow? Is that refrigerant? Has the compressor just started to have poor windings and it's got ohm values are much higher than it's supposed to be because the drive is now seeing that the the wattage on that unit is much higher? You're going to have bad defrost cycles in the wintertime, right? It's just, if we can't move refrigerant, we can't add or remove heat. That simple, right? Might start getting some reversing valve issues. Reversing valves require a pressure differential, right? And if we have too high of a pressure differential, that little bathtub plate, that little Teflon plate in there, it could start leaking. And then we've got hot gas going right back into our compressor. That's even worse, right? TXV's issues, yeah, the TXV can get stuck. It can get stuck wide open. It can get stuck closed. Obviously, we're going to have a compressor failure. And not as common, but it could happen. Get some refrigerant leaks. We start building up that high pressure, high temperature gas in our outdoor coil, and we start bouncing off that head pressure on and off. Yeah, we can expose a weak point, right? So we're talking about all this. What can we do? What are things to look for? Do not use flex duct where an elbow should be. Never. Never should you take a flex duct and make it into a 90. Use hard elbows. Like I said, you ever go down a curly slide? Imagine if that curly slide had all sorts of bumps and ridges. You're not going to go around that corner very fast, right? And the same thing with our airflow. If you use flex duct, make sure it's pulled tight. I mean, if you go up into an attic and you see flex duct, just grab it and pull it towards you. See how much you can pull out of it. It's pretty embarrassing to see how often we can actually connect point A and point B in a box. And then there was one scenario, I wish I still had the picture. I had an installer actually open the box on both ends of the ducting and connected point A and point B and left the box in the middle. I couldn't believe it. We want to avoid sags and flex duct, right? We want to make sure we have proper supports. Um, Bigger is not better. Do not oversize equipment. Long run times. We got to have a proper run time to remove that latent load in the home, that humidity, right? If we don't do that and we're not actually exchanging the airflow, it's not going to work, right? CFM, cubic feet per minute. Anybody that's used to doing blower door testing knows we're talking about air changes an hour. If you take a home that's, let's say the home is 2,000 square foot, right? 2,000 square foot home. And let's say it averages 10-foot ceilings. That is 20,000 cubic feet of air in the home. So take a little box, a little cubic feet of air, and you put it in the home. There's 20,000 of them, right? And if it's a 2,000 square foot home and we've got a 3-ton unit moving 1,200 CFM, that means it's going to have 16 air changes an hour. That's a lot of air changes. So how many times do you think the air is going to have to be supplied to those back rooms to actually reduce the heat? Because like I said, we're adding or removing heat. That's all we're doing. And we can't do it if we're not removing refrigerant, if we're not moving airflow. So do not oversize equipment. Verify filter sizing on the problem, on the filter sizes on the systems are proper. And yeah, filters do have a maximum CFM rating. And if you don't know, you're not looking hard enough. The air information is out there. And obviously do proper startups. So it's just a charging chart for some of our MERV 8 filters. 16 by 20. Look at it. Look what it's able to be rated at, 300 feet per minute. That's our velocity. 1625s, 20 by 20, 20 by 25s. They do have a limitation, right? And this will vary based off what your velocity is, and your velocity will change based off of your ductwork. It'll differentiate based off of what your resistance in your ductwork, how the ductwork was sized. And seems like nowadays, new construction builds, everybody seems to be sizing their systems differently. But if they're not sized for the filter, it won't work, right? So you start looking at our clean effects. Please only put clean effects on variable speed systems because the constant CFM blowers are designed for that. Uh, it's really hard to have a conversation with one of you guys over the phone that maybe that clean effects, as awesome as a filter of it is, maybe it wasn't the right application. right? So you start looking at the sizing and you look at the sizing charts, you start looking at the pressure drops at certain CFMs. Obviously, we can't take one of those 145s and put it in a 245 application at 2000 CFM and expect it to work. The pressure drop will be so great that although we are moving the air, we're not be moving enough, right? So the best filter in the world is a piece of cardboard that no air can go through it and no dirt. But then our systems don't work, right? So we're just trying to fight that battle between proper airflow and having enough airflow. And our startup sheets, our data collection sheets, I cannot stress enough how important this is. Um, it's really, really, really difficult for us to support no information, right? Airflow is not just good. It's not a four-letter word. It's a number, and we need that number. All this information, as frustrating as it could be to have this information, it allows us to help and assist you guys. So something as simple as filling out this sheet, and then I look at it and go, wow, our airflow is great. Our static pressure is great. We are moving the right airflow. We have the right filter. What's our suction pressure? What's our liquid pressure? And then I might catch something on this sheet that says, oh, superheat at 1 degree. Wow. And our subcooling's kind of low. I'm wondering if maybe that metering device is stuck wide open and we're just flooding that coil, right? So it's this kind of information that could be the difference between you having to go back to that site time and time and time again. So please utilize these sheets. If you don't have them, let us know. We'll get them out to you. Um, if you get a system that's just difficult, right? Send your tech out with this. Say, hey, I need you to go out there. I need you to get all this information for us. So when we call tech services, we have this information. And really, you should have this information on startups too. If you don't have it, please start doing startup sheets. So, main takeaway for today: airflow. It must be established and set before charging any outdoor unit, or it will be incorrect. I cannot stress that enough. If you do not move the airflow, we cannot move the proper refrigerant, which means we cannot have a properly sized, properly working system. You might have sold that customer a 3-ton, but are we actually running at 3 tons of capacity? Verify the indoor blower settings are correct. They are not set up from the factory. You have to set them up. There are multiple speeds and multiple settings for a reason. It allows you to set them up for the home. Variable speed systems, set up the airflow, set it up using the app. Let's verify that it's actually doing what it's supposed to do. Run the system in cooling and heating airflows, right? Let's just operate it. You might have a system you're installing in the middle of winter, run it in cooling real quick. Let's just make sure that our pressures are stable and that we're not having an issue with a metering device not flowing back and forth. Perform total external static pressure testing. Verify what the resistance is in the ductwork. You can plot that CFM and plot that static pressure on the service facts to see what our CFM is. That's what the manufacturer wants to see. That is what Trane is going to want from us when we tell them about airflow and its problem system. They're going to want to know what the speed tap is, what the CFM settings were, what our static pressure was, and where that number lands on that chart. Even if you use a true flow plate, that is great. Still need that information, right? A true flow plate does not give you an excuse not to do static pressure. We have to do that. And obviously, charge the outdoor unit once all the airflow is set. And we are charging at 400 CFM per ton. So let's really keep that in mind. Now, does anybody have any questions? Feel free to fill out the survey. I'm looking at the chat. If anybody has any questions, please feel free to type them in there. If it's something that can help the whole team, I'll be more than happy to read that information out. If it is something that needs to be addressed. Looks like I had a question. Let me see. Levi, I think it was Levi that was on there. Whoop, what happened? Make that go away. Okay, any other questions? I will answer them as they come through. Let's see any. Go ahead and type them in the chat and I will be happy to send those out. All right, guys. Have a good day. Please remember to do your airflow checking. Check your charge, check your airflow. All right, thanks, guys.